Hi,
Yes, we can hear you. All right, so next speaker will be Song, and he will tell us about scattering of particles and strings from surfaces. So please take
thank
it away.
you. Thank you for the introduction, and I'd like to thank the organizers, Daniel, Jiaxian, Yuting, and Samin for putting together this wonderful workshop. I'm really sorry that I couldn't be there in person. So today I'm gonna talk about some works that have been done with Nima, Carolina from Princeton, and also two students, Chi and Jing from Beijing. Which are really all of these are really outstanding students, and Jing is applying this year. I think last QCD Meets Gravity, I've focused on these two papers on hidden zeros, factorizations, and um, uh, deformation into nonlinear model and Yang-Mills. So today I'll be mostly talking about more recent works on how to get all loop integrands in Yang-Mills and some other work in progress, as well as some paper to appear with Qi Jing and also Fan that concerns going beyond just pure Yang-Mills theories. Okay, so I'm sure you've heard a lot, especially in Yara's review, that there are numerous positive geometries underlying scattering amplitudes and other physical quantities. They can be in some auxiliary space, such as modular space or positive Grassmannian. They can also directly live in kinematic space in some special theory, such as the M2 hedron in n equals 4 super Mills or ABGM theory. And also there's this a potential geometric object for half BPS correlators, which contains in the Lilac limit also the squared amplitude hedron that you've just heard that can give you the integrand for energy correlator, as Kai told us. And most relevant for my talk today will be some positive geometries, or rather polytopes, and their underlying combinatorial structures for theories living in general dimension without any special theories that's n equals 4 supermills and so on. So the first one is this social hedron in kinematic space for the bi-adjoint phi cube tree amplitudes and the corresponding worldsheet social hedron for open string modular space. And I'm sure you heard from Julio that there's this all loop generalization of the hedron and the string amplitudes based on this surface hedron for phi cube and also the underlying curve integral for the string theory case. There are examples for cosmological cases and also other applications that I won't get into. So my talk today will be based on this so-called curve integral formalism on surfaces, which is essentially combinatorial. So the polytope structure here is not the most important one. It's actually the combinatorial one, which give you a curve integral, which but in the field theory limit that correspond to some polytopes. But in full generality, at finite alpha prime, this will be some bosonic string for, say, tachyon amplitudes, which in field theory limit corresponding to all loop amplitudes in trace phi cube. They are the simplest colored theory, where essentially the amplitudes are determined just by long distance singularities. So I'm sure you heard from Julio's talk. But the question is how to go to more realistic theories where you not only need all these poles, but also have numerators, right? So already you can contrast phi cube with more general coupled scalar theories, or much more so when you go to pions and gluons. So this curve integral formalism seems to provide us with a new formulation that's entirely based on surfaces, which can give you not only this trace phi cube and underlying bosonic stream, but also seems to be very general. So what is this formulation good for? I think I can at least list these 5 points. The first one is that already at tree level, this gives you manifest factorizations based on these curves on surfaces at finite alpha prime. So these are factorizations at any massive poles. There's no need to blow up in the worldsheet that you can study the residues at any massive level for finite alpha prime bosonic string amplitude. And at loop level, uh, I'll just mention, I'll just focus on alpha prime to zero limit. This also manifests not only the factorization, but also the loop cuts, which essentially give you some all loop recursion relations for trace phi cube or more general colored scalars. And in the last year, I've talked about these two other things, which is the unity of Chase5Q with nonlinear Sega model and Yang-Mills. It seems that at least at tree level, all this theory, all these amplitudes are unified in a single curve integrals at tree level, the single kinematic function, just at different positions, and they also manifest some properties such as hidden zeros and the splittings near the zeros for all these theories. And in particular, for nonlinear Sega model, it's just done because this immediately generalized to all loops that you can once you obtain the all loop Chase5Q integrand, you can do some shift and obtain the all loop nonlinear Sega model integrand. So for gluons, it's much more complicated. You cannot just take the field theory limit, the Chase5Q theory to try to get gluons out of it. You have to go to the stringy Chase5Q, which you need the full juice of these curve integrals on surfaces. And the claim is that once you do that, the all loop Yang-Mills integrand are still contained in this stringy Chase5Q. So this theory, I'm sure most of you are familiar with, is just the simplest colored theory where the scalar phi is described by n by n matrix. And the natural Feynman diagrams here are actually these fat graphs where you can view them as each fat graph, the cubic Feynman diagram in this fat graph form can be viewed as a triangulation of the surface, right? This is a tree level case where you have the triangulation of a 5-punctured disk. And this is a one loop case. You have a 4-point one loop case. You have this fat graph, which is like a triangulation of the one loop 4-point case. And the kinematic is that for each chord here, for each curve here, you have some sum of the momentum squared, which is the kinematic variable. Say at tree level, this is really just all this planar pose you can have in Chase5Q. So the tree level amplitude here is really the sum of all possible triangulations of the n-gon, which is also the canonical form of an isosahedron. Like 4-point, you have the 1 over s plus 1 over t. For 5-point, you have 5 triangulations, each with 2 planar poles. And the non-planar Mandelstam variable we denoted as Cij is this combination. So let's go to finite alpha prime. So in the finite alpha prime case, this isosahedron for Chase5Q is encoded in the original Veneziano-Koba-Nielsen formula. This is literally the n tachyon amplitude, just with the kinematic variables shifted by 1. You can imagine that go to level 1. And it's also known as the z integral in the z theory. You have this Park-Taylor factor and this Koba-Nielsen factor. So the crucial thing is that you introduce some u variables, one for each chord in this disk. And the u variables are nothing but this special cross ratios from the worldsheet point of view. So once you introduce u variable, the Koba-Nielsen factor immediately becomes all the u variable to the power of this planar variables I just introduced you for every curve, right? And then this Park-Taylor form is also very nice. You need to write down, you need to introduce some positive parameterization. Then the Park-Taylor form is nothing but the d-log form of this positive parameterization. And the u will be given as some positive polynomials, ratio of positive polynomial of this y's. So this will be the curve integral that I'm talking about for the tree level case. For example, for 4-point, the Veneziano amplitude is now written as dy over y, this u13 to this power and u24 to this power, which is the beta function. So what is this good for? The first thing is that you can see that at any massless or massive pose, xab equals any non-positive integer, its only contribution is coming from this uab goes to 0, okay? But since there's this u satisfy the u equation, when uab goes to 0, all the incompatible u goes to 1, then the amplitude immediately factorizes into 2p's. I mean, at the massless pole, this is literally the scalar factorization. But at a massive pose, later I will come to this point that you'll see some exchange of massive string states, but it's still the same factorization manifest by the u variables. There's actually a beautiful description using this surfaceology also for all possible orderings and possibly going to the closed string case, but that's for another talk. So I won't go into details for the zeros and splits since I've talked this last time. I just want to mention that when you set some of this non-planar variable Cij, the Mandelstam non-planar Mandelstam variables to some integer, the amplitude vanishes. These are the zeros of the string amplitudes that people have known since the 70s. And this y curve integral form makes it completely manifest. And more than that, you can see that if you turn on one of the C away from 0 or from a non-negative integer, there's a factorization near such zeros, which is really the string amplitude factorized into two currents times a 4-point intermediate one. And this 4-point amplitude will vanish when you turn the last one into integer. So that's the zeros are implied by this splitting behavior. And there's really a lot of works on this hidden zeros and their splittings, also for Yang-Mills, for GR, for bosonic or superstring. And very nicely, since these zeros and splitting are for the colored case, not only for phi q but also for pions and gluons, you can see that they have to be unified together. So there's a simple deformation on top of the original phi cube amplitude. If you deform it by this factor, which is all the u even divided by u odd to any deformation parameter delta, this is amounts to just a kinematic shift. You are shifting your planar variable even by amount of delta and odd by minus delta and keeping all the even odd untouched. So this very simple shift is the only shift that can keep all the Cij unchanged. So this shift is guaranteed to give you some amplitude that also preserve all the zeros and splittings. Turns out very nicely that this shift gives you nonlinear scalar model and Yang-Mills for generic values of delta, and the delta equals integer. I mean, equals 1 is give you Yang-Mills scalar, but equals 2, 3, 4, they give you higher spin massless particles. So we'll only focus on the Yang-Mills scalar case. So just by starting with 2n point trace phi cube scalar theory, do this simple deformation, you get nonlinear scalar model and the 2n scalar which contain n gluon amplitudes for free. So they are all described by the same function evaluated at different kinematic points. Okay, so I also talked the last time that this nonlinear scalar model is also this deformation is also true to for at loop level. So once you have the trace phi cube integrand to all loop level, you can do this same deformation now involving also the loop puncture. So remember here, since you are deforming it as a generic delta value, when you take alpha prime to 0 is equivalent as taking delta to infinity. So you're just taking the field theory trace phi cube and do this deformation, send delta to infinity, you get all loop nonlinear scalar model for free. So this is without the need of all the stringy business. And it's a very practical thing. I just want to mention that, for example, you can use this to get 4-loop nonlinear scalar model integrand if you're interested. Now come to the gluons. So for gluons, the story is much more complicated because it's at delta equals 1. So this changes the singularity structure of your dy over y. Actually, it changes from dy over y to dy over y squared. But I'll give you a more familiar derivation that this is indeed the 2n scalar amplitudes in bosonic string. Since you can take the original bosonic string 2n point amplitude and go to this special configuration where you have only the epsilon 1 dot epsilon 2, epsilon 3 dot epsilon 4, and so on to be 1, and all the other Lorentz contraction involving polarization to be 0. So this actually gives you exactly the phi cube, trace phi cube string integral, the tachyon amplitude multiplied by this ratio I mentioned, that delta equals 1. Okay. So this gives you a very nice opportunity that you look at a single term, which is just the deformed guy with delta equals 1, and taking these residues allow you to extract n gluon bosonic string amplitude out of the 2n scalar amplitudes. So this is known as the scaffolding. Okay, so every gluon is described by a pair of scalars where the momentum of the gluon is the sum of their the sum of the two momenta, and the polarization can be chosen to be the difference of the two scalar momentum. So the formula looks like that. Our deformation just simply makes the dy over y into dy over y squared, where this external this n scaffolding variables will eventually be taking residue. So from 2n scalar, by taking this n-fold residue, you get n gluon, and the inside the n gon, you still have the dy over y squared for all the gluons. So this is a scaffolding picture. After you're taking the n-fold residues, you turn this 10-point scalar amplitude into 5-point gluon amplitude, but now written in this X language. So for example, the 3-point gluon amplitude everyone is familiar with now is expressed in terms of as if there are 6-point scalar amplitude in terms of this x variables. So this first piece will be the Yang-Mills 3-point amplitude, and the second term is the f cube, just product of three x's. So this formulation is already very nice at tree level. It gives you a new formula for all this tree amplitude now without epsilon, right? Now everything is written in terms of this 2n scalar x variables. And things we are familiar with, such as gauging invariance and the gluon factorization, become completely manifest in this formula. So you can take the n gluon amplitude has to look like this to be multilinear and gauging invariant in every gluon. And also, if you go to an xab equals 0 pole, now it's not a scalar factorization. Now this dy over y squared turned into a gluon factorization where you have some propagating of intermediate gluons. So this is the tree level story. And now I'm moving to more recent work that we want. The real advantage of using this curve integral formalism is allow you to go to all loops. So the surfaceology, since you can do stringy trace phi cube to all loops, it's very natural to think that just on any surface, you just change the dy over y into dy over y squared, still the u to the x on any surface for the 2n scalar formula. Should then after you take in the residue, it should give you the n gluon at any surface, at any loop order. Of course, now unlike tree level, now you have all these self-intersecting curves and also the closed curves. So for example, at one loop level, you need to include the self-intersecting once curve and the closed curve. And I want to emphasize that this is still much simpler than the actual bosonic string loop amplitudes. But we conjecture that this all loop form with dy over y squared indeed give you the all loop Yang-Mills integrants in the alpha prime to 0 limit. So you don't need a full-fledged bosonic string. And there are many checks. Of course, you can check that at loop level, there's also this notion of gauging invariance and factorization or cuts. You can explicitly compute one loop Yang-Mills integrants out of it. The higher loop integrants is still quite difficult if you want to take the alpha prime to 0 limit on higher genus surfaces. But you can actually show something very nice already. You can compute all loop leading singularities, which is the gluing of 3-point vertices, the 3-point vertices including Yang-Mills and the f cube in this X space. So there recently has been proven that if you choose this closed curve delta to be 1 minus d, whereas this d is where the dimension start to appear in your formula, you indeed get the residue or the maximal residue of this formula is giving you all the gluing of 3-point amplitude. So in this way you get automatically get all loop leading singularities in the thing. But if you want the full integrand, there's still challenge, right? If you want the full integrand, then I want to mention that in principle it's very similar. Just as you reconstruct all the tree amplitude out of factorization, now you need to reconstruct loop integrand from cuts. But it's famous that the forward limit of tree amplitude in general dimension for pure Yang-Mills diverge, right? So here's the surface is you really gain a lot by considering the surface kinematics, because the surface kinematics provides you these variables also for the tadpole and the massless bubble propagators, which is a naive divergent thing you encounter in the forward limit. So it's a little bit like the tree level when you double the kinematic variables for going to complex kinematics in the four-dimensional tree case. Here you also double your number of kinematics, which provide you a natural regularization that you can directly take forward limit of tree to get loop integrants. So in this way, the surface actually make it clear that even to all loops, there is some preferred integrand defined in terms of the surface kinematics, which will tell you that this integrand actually enjoys some surface gauging invariance and surface factorization or cuts. So for example, you can compute the one loop single cuts of the surface integrand in terms of the forward limit of tree, and then reconstruct the full integrand using residue theorem. Of course, this is still very troublesome when you go to higher and higher loops, involve too many variables. So one way to do it is to discard all the scaleless integrals. In this way, we could run this mechanism of loop recursion and obtain, say, up to 2 loop 6-point pure Yang-Mills integrand. At least at one loop, we can also check that this integrand give you the correct integrated answer after you do some integration. And to seek for further simplification, you may want to go back to external data living in 4D using the spinor helicity. But this is generally still an ongoing program of generating from forward limit or the higher loop Yang-Mills integrants. The next, I will talk about some ongoing work to hopefully to appear soon, that we also want to include fermions and in a more general gauge theories, and also for the super Yang-Mills case. So everything I've talked about live in general D dimension with external gluons, but you may wonder how can you add fermions in the loop? So actually, this is already in some work in some work several years ago with Alex and collaborators. There's already seen some very nice structure when you take forward the limit of tree amplitudes, not only with a pair of gluons, but also with a pair of fermions or scalars. So since you can expand your tree amplitude in terms of some simpler scalar line building blocks with these prefactors, once you do forward limit, you just turn these prefactors into some vector chase of few strings or some spinor chase of few strings. And this gives you the one loop, the single cut of a one loop amplitude, either gluon running in the loop or fermion running in the loop, right? So back then, we used this as a starting point of getting, say, like linear propagator one loop integrand. But now we have the surface reconstruct all the one loop integrand from the surface, which is no longer need this linear propagator business. So you can recycle this result and get a very nice formula already for the pure Yang-Mills case. You have a one loop universal expansion. So the one loop n gluon amplitude is expanded into some prefactor times the scalar loop objects. Here are some examples. So where the scalar loop objects are just with some blobs of scalars and gluons on the outside, but in the loop it only scalar runs, and all the dependence of the gluon loop is in these prefactors actually. So you only need to consider the simplest case where it's actually in the large D limit. It's a scalar loop with only gluons on the outside. This A empty set is the only thing you need, and then everything else, all this other scalar loop can be obtained by some differential operator acting on the polarization. They just give you some mixed amplitudes. The real payoff of this formula is that now you just immediately turn it into a formula for one loop integrands or one loop amplitudes in general gauge theories. All you need to do is to use the same scalar loop objects, but turn the prefactors from some Lorentz chase to a combination of Lorentz chase with spinor chase for any multiplet. So now you can in the loop you can run anything you want, and in particular for the empty case it can depend on the number of vectors, fermions, and scalars. So this is in some sense some effective SUSY word identities that for any multiplet running in the loop, you express them in terms of a scalar loop object times some general prefactors depending on the chase, right? So for example, if you plug in that the number of gluon vectors and fermions are for the maximal SUSY case, you see huge simplifications. Like any of these prefactors with m less than 4 is immediately 0. This is the famous no triangle or bubble tadpole property for maximal SUSY, and also for the correct power counting when you have box or pentagon and so on. So of course the question is that we do have the forward limit recursion for pure Yang-Mills to higher loops, but we don't know how to do this, how to include fermions and so on at higher loops. And also this result, of course, will not immediately satisfy color kinematics duality. So before the thing is that you want to basically bootstrap. You want to find some BCG numerators, and we can do this for pure Yang-Mills up to 6 point or super Yang-Mills up to 8 point. But maybe there's really a better way that you can directly get the gravity amplitude without going through the strictly the BCG satisfying numerator. So how much time I have?
5 minutes.
Okay, great. So in the last several minutes, I will mention something that's very preliminary that we're thinking. So everything I've talked about so far are mostly using this curve integral at tree level and loop level as a way of generating all loop integrands in Yang-Mills theories, and including some one loop results for general gauge theories. So I want to talk about something that already at tree level, I think is quite interesting, that this curve integral also makes it very easy to compute, extract these massive string states and massive string factorizations. So just as you get the gluon case as a scaffolding of dy over y squared, here you can also get massive string states by going to these residues, right? It's very similar to the scaffolding. You take this xii plus 2 variable equals not 0 now, but -1, -2, and so on. That amounts to taking case derivative at this of these u variables. So for example, at level 1, now you see this dy over y squared, and that gives you a kind of a vertex operator that the level 1 you have this spin 1 particle times some worldsheet u dependence. So this formula looks exactly like the gluon case, except now you have a x13, which is no longer 0, but -1. You can go to higher levels. Like if you go to level 2, you need 2 derivatives, but it's very simple that you get a term which is v1 squared and another term that's second derivative. So you can keep going, and at any level k, you create this massive string states of higher and higher spins and so on. Mixture of higher and higher spin massive particles. You can also do it for more than one string state. So it's literally looking at this, looking similar to the scaffolding picture that at every pair of scalars, you can start to create some massive level n1, n2, n3, and so on. And that involves not only this V for individual particle, but also W for a pair of particle. But that's it. There's no like triple or anything. So all you get is a formula of n massive strings scattering at tree level, which is a product of this V and W formula with a total degree that agrees to the mass level. So for example, these are 3-point case where it's completely external. For 4-point case, you also get some polynomial in terms of these x variables times the original massless Veneziano amplitude. So this is just a very easy way to extract some massive string amplitude, but you want to really see what's the physical meaning of them. So you want to compare these residues with some worldsheet calculation. At least for leading trajectory, I think there's a very well-defined comparison. But the real question is if we can make sense of all the string states, if we can use this scalar scaffolding way to label as a new method of label all possible massive string states in this way. And also you can go to not only just the external massive string, but you can go to an internal one where you see the general XAB at the mass level. The formula makes it completely manifest that you exchange the level K massive string states. So just as level 1, this is the same factorization formula as we shown for gluons, except now you have a massive spin 1 particle propagating. And it's even more interesting if you go to closed string. Now you start to see some non-planar poles at this massive level. Even if you start with the ordered Park-Taylor mod square integral, you start to see some very interesting residue at non-planar poles. And finally, I want to mention that everything so far is for bosonic string. We've also started to thinking about superstring, where after you integrate over this worldsheet theta Grassmann variable, you get a Pfaffian. So this Pfaffian, in terms of the Tu and Gong variables, looks as some correction to the bosonic string. So the first term is like the original bosonic string, and now you see some other terms which their job is to cancel, for example, this F cubed term to give you already tree level leading singularity is purely the gluing of Yang-Mills. So this is just a start. We still don't know if there's an intrinsic way of formulating superstring using the curve integral formalism. Okay, so I'll just summarize that we've seen that the trace phi cube is described as some positive geometry now as surface hedron, but the really more important thing is what's behind it is this curve integral, which allow you to also go to pions and gluons and so on. And there are many things to explore. For example, in the world of zeros and splittings, I would say most of the studies are being focused on tree level, tree amplitude zeros and so on, but there are really also loop level zeros and splittings. Whether or not they have physical meanings, I still have no idea. And for this all loop recursion for Yang-Mills, conceptually, I think it's just done. That there's this keep taking the forward limit of higher and higher loops, but how to put it in a practically usable form is still a big question. And I have not talked about gravity, but at tree level or at leading singularity level, there's not really many really new things because you're just squaring things. It's really the question is, can you extend this loop level curve integral case to the colorless case, which will make it the diffeomorphism invariance and also all the factorizations, including non-planar ones, all manifest. And finally, I want to say that even understanding tree-level string amplitudes, including closed string and also superstring, and especially as a tool of probing all these massive string states, would be, I think, very interesting future directions. Okay, that's all I want to talk about. Thank you.
Yara?
Hi, Song. Thanks a lot for a nice talk. Can I ask you on how practically do you calculate the cuts for the Yang-Mills integrand in the y variables? So there is y over y square poles, but there are also u's.
Yes.
How do you take the residues in practice on these y?
Yeah, so if you want to calculate leading singularity, then you take maximal residues. That's very simple. So you have the formula, and there's no alpha. So there's no integral to perform. You just take residues all the way to the end. There's even combinatorial formulas. But for general cuts, it's still quite troublesome. So we haven't studied like unitarity cuts and all those things. All we are using are the single cut, right? So if you take a one loop formula and take a single cut, you get something. And then the job is to compare with the forward limit of the tree object. So that agreement is the first thing we in the alpha prime to zero limit. This is the first thing that allows us to build the one loop integrand out of this. But we have not systematically studied anything between leading singularity and the single cut. I think they are all doable. It's just the leading singularity, there's no alpha prime to zero limit to take. And for single cut, is just in the alpha prime to zero limit, you can compare it with the forward limit of tree. But anything in between is also doable. It's just that we haven't looked into them. Yeah.
There are other questions? Okay, if not, let's send both speakers again.
Thank you.
So unfortunately, we have to close the auditorium at 5. So yeah, so please move to the 7th floor of La Cospa, which is hanging around the city. So see you tomorrow.